8.2 is confidence intervals for population mean when we know the population standard deviation. So we've got some more vocabulary. We're going to look at confidence level, alpha, but we're going to do that on the next slide. Now with the confidence interval, we're going to have what we call a two-tailed test. So when they give you the confidence level, like let's say they give us 95% confidence level, that means that the 95% is in the middle and we have two tails. And so in order to read the Z tables and in 8.3 the T tables, we have to find how much area is in just a single tail. So what we're going to do, we know that the entire amount is 100%. So let's go ahead and change our 95%, our confidence level, to a decimal. And now we want alpha. So alpha kind of looks like a fish there. Alpha is going to equal 1 minus the confidence level. So if we have 95% as our confidence level, we're going to take 1 minus 0.95. Well, that gives us 0.05 or 5%. But that 5% has to be split into both tails. It's not just one tail, because otherwise we'd have too much. We'd have 5% plus 95% plus 5% would get us over 100%. So what we're going to do is we need to take that alpha and cut it in half because we want two tails. What that tells us is that in each tail, we're going to actually have 2.5%. And this is because of symmetry also, right? With a normal curve, it's symmetric. So if I've got 95% in the middle, I've got to have the 2.5% on each end. So that's important when we start looking at the Z tables and in 8.3, the T tables. Okay, so we have a formula here. This is on your formula sheet as well. The margin of error, this time we have to use a formula or use GeoGebra because we are not going to be given the confidence interval, we'll be finding the confidence interval. So 8.1, we worked backwards. But here, if we're going to use the formula, we have to first find Z of alpha over 2. So of course, they're going to give us the confidence level so that we can find alpha, and then we have to divide alpha by 2. And that way we can look up the Z-score and the table. Because remember, the area is the alpha and the alpha divided by 2 and the confidence level. But the Z-score is on the number line. So we have to look that up from the table. And then they're going to give you the population standard deviation, sigma, and they're going to give you the sample size. So it's easy enough to plug this into the formula at that point. Now, when we're interpreting the confidence interval in some of these problems, what we're going to do is say, let's say it's 95% confidence. With 95% confidence, the population mean is somewhere between our lower limit and our upper limit. And it'll just depend on the confidence level. But we want to be confident. Make sure you pick the answer that has confidence in it. And then it's the population mean. We already know the sample mean is between those two numbers, but we're looking for the population mean. All right, now in GeoGebra, we have to go somewhere a little different than we've been doing. In the last chapter, we went to probability, and then we stayed in the normal distribution that came up, or we switched it to binomial or Poisson. This time, though, for confidence interval, we are going to click on the statistics tab, and then we have to change the menu here. It's going to always come up as Z test of a mean. We're going to test later, but right now we're looking for estimate. So we need to change it to Z estimate of a mean. That's going to give us our confidence interval if we know the population standard deviation. And then we can put in everything we know. We're going to put our confidence level, we're going to put the mean, the population standard deviation, and N. Now this is kind of a misnomer. This is supposed to be, it's actually an error. needs to be a lowercase n because it's a sample size, not a population. Capital N would be population. The other thing is the question marks stay put. So make sure that you delete the question mark before you type in your data. Otherwise, it's not going to take it. It's not going to be happy. So we'll put in the confidence level, the mean, the sample mean, the population standard deviation, and the sample size. And GeoGebra, like magic, is going to give us our lower limit and our upper limit. So it's going to give us the confidence interval. All right, so let's take a look here. We have the length in inches of adult corn snakes are normally distributed with a population standard deviation of 8. Okay, so that's sigma. Sigma's 8. And an unknown population mean. That's what we're trying to figure out what that's going to look like. The random sample size of 25 snakes, so n is equal to 25, is taken and results in a sample mean, so x bar, of 58. Identify the parameters needed to calculate a confidence interval at the 99% confidence. Okay, so let's see what they want here. They want the sample mean is the first one, x bar, so that's 58. They want the population standard deviation, sigma, is 8. Sample size is 25. Now they want z of alpha over 2. So we have this nice z table here, but we need to find alpha over 2. So what's going to happen, and we don't have to draw this every time, but we've got 99% here in the middle. And we need to know how much is in each tail so that we can go to the table here. So what we're going to do, alpha is equal to 1 minus the confidence level, but I'm going to change it back to a decimal. So that tells me that I'm going to take 1% and split that up into each tail because I already have 99%. So 1% is going to go into each tail, but I have to divide that by 2. So that gives me this teeny tiny bit. It's going to be 0.5% is my alpha over 2. So if I come here to the table, the z value for 0.005 is 2.576. And they do want all 3 of those decimals. Even though they say you're going to round to 2 decimal places, that's for the final answer. Okay, so we could use the formula. We could find the margin of error E. We could subtract it from the sample mean and add it to sample mean, but we have GeoGebra. So we're going to go into GeoGebra. We're going to go to GeoGebra Classic. We're going to hit probability, but when we see the normal graph, we're going to hit the tab for statistics. And then we're going to change the drop-down menu to Z estimate of a mean. That's how we're going to get a confidence level, or confidence interval, excuse me. And then we're going to put in, we don't even need the Z, but the problem's making us do it. But GeoGebra doesn't make us do it. So we're going to put in the 99% confidence. We're going to put in our sample mean, our population standard deviation, and our sample size. And look what happens down here. It is going to give me the answer. It's going to give me the lower limit and the upper limit for the confidence interval. So I'm going to come back down here. It wants 2 decimals. So I'm going to do 53.88 is my lower limit, and 62.12 is the upper limit. And that's it. Yay, GeoGebra. All right, this is the same data. We've got the population standard deviation of 8 inches. We have the random sample of 25 snakes, the sample mean of 58 inches. And we found the confidence interval, but we want to interpret it now. So we always want to be confident. Therefore, we're not going to use this last one because we want to be confident. And then the point is that we are 99% confident that the true population mean is between these two numbers, not the sample mean. We already know the sample means between those two numbers, but we're looking for the true population mean. And again, the larger the confidence, the wider the interval is going to be, because we've got to give ourselves real room if we want to be 99% confident. So when you're watching all of these graphs and charts that they show in the news, make sure you take a look and see how confident they are, because they can tighten up this confidence interval and just say, oh, well, I'm 70% confident. But that's in the fine print. Okay, let's do a whole nother problem just like this. So suppose weights of running shoes are normally distributed, have a known population standard deviation of 1. So sigma is equal to 1. A random sample of 24 running shoes, so that's our sample size n, is taken and gives a sample mean of 13 ounces. So sample mean is 13 ounces. Identify the parameters needed to calculate a confidence interval at an 80% confidence. So that's 0.80. Okay, so the issue is over here, if we want 80% in the middle, then we have to split the rest into each tail. So it's kind of easy to see that that's 10% and 10%, but let's go ahead and do it. So we have alpha equals 1 minus 0.80. So that leaves me with 20%, but I need half of that because I need to put half in each tail. So I want z of 0.10. That's going to be right here. And I'm going to go ahead and put that in while I'm here. All right, let's fill in everything else we know. We know that our sample mean is 13. Our population standard deviation is 1. Our sample size is 24. And then we're going to come over here. I already put it in GeoGebra. So I went into probability. I hit statistics. I changed the drop-down menu to Z estimate of a mean. This is very important. I put in my confidence level, the sample mean, the population standard deviation, and the sample size. And out popped my confidence interval. So I have 12.74 as my lower limit, and I have 13.26 as the upper. All right, but you have to change that drop-down window, and you're going to know that you have to change it because it's going to start talking about a null hypothesis, and we haven't done that yet, and that has nothing to do with the confidence interval. All right, now we're going to interpret all the same data as the page before. We know we want to be 80% confident, and we're looking for the true population mean. So it's going to be the first one. Second one doesn't work because there's no confidence. We want to be confident. And the last one doesn't work because we don't want the sample mean. We already know the sample mean's in the middle. It's the midpoint. We're looking for the population mean. Now, some of the problems don't even make you use the z-table at all. They just want the confidence interval, and it says you can use a calculator or you can use the common z-values above. So we're going to use GeoGebra, but let's take a look at the problem. Suppose scores of a standardized test are normally distributed and have a known population standard deviation of 11 points. A random sample of 15 scores, so that's my sample size, is taken and the sample mean ends up being 101 points. We want to find a 98% confidence level. So if we only use GeoGebra, we don't have to convert this. We don't have to try to find alpha over 2 because we're just going to put the 0.98 right into GeoGebra. Just make sure you got to click on statistics and you have to change this drop-down window to Z estimate of a mean. And then you can put in everything from the problem, the confidence level, the sample mean, the population standard deviation, and the sample size. And then GeoGebra, like magic, spits out the confidence. We went 2 decimal places. So 94.39. Make sure you check the fine print because sometimes they want you to round to the nearest integer, which if that's positive numbers, that's just the whole number, right? We're not going to have decimals. If it's negative numbers, same thing, we're not going to have decimals. Sometimes they want 1 decimal place, sometimes they want 2. Some of the problems in 8.2, they're going to give you the raw data. They're not going to give you the sample mean. They're going to give you the population standard deviation, but they're not going to give you the sample mean. So what you're going to do, because sometimes it's a lot of data, like this is 38 pieces of data. We don't want to find the average in our calculator for 38 pieces of data. So what you're going to do is you're going to click on copy to clipboard. That's going to save all 38 of these pieces of data so that you can paste it. Okay, so you're going to click on copy to clipboard. Then you're going to go into GeoGebra like we normally do to find mean. You're going to go to GeoGebra Classic, Spreadsheet, and then come over to A1. I scrolled down a little bit, but come up to A1 and click Control V. When you do that, it's going to put a title in the first box. So it's going to put time in the first box because these are commute times. And then it's going to put the 38 pieces of data. When you go to highlight your data, don't use the first box. Don't highlight time. Go ahead and click down to A2, and you're going to highlight A2 all the way down to A39, or however many pieces of data you have. So highlight your data, and then like we've done before, you're going to click on the histogram, one variable analysis, you're going to hit the sigma x, and it's going to give you the mean. Now I went ahead and used 2 decimal places. I probably could have just used 1, but I always like to use a little more than they say. So when I go into GeoGebra probability, I'm going to put in the 27.61 that I found using my raw data. And then I had to put the rest. It said the standard deviation is 4.5. The random sample, so sample size is 38, and the confidence level is 98%. It says to use Excel, but don't worry about that. We're going to use GeoGebra. So you put all that in. You put everything in that you know, and it is going to spit out the confidence interval. But for this one, it says round your answers to 1 decimal place. So for the confidence interval, they only want 1 decimal place. And that's our answer. Hopefully it's starting to look pretty good. It's just that if they give you the raw data for 8.2, you're going to have to find the sample mean. For 8.3, you're going to find the sample mean and the sample standard deviation. But we know how to do that. We've been doing that also. All right, this is just another example. There's 70 of these. So we're going to copy to clipboard. Once you click that, then you can go into GeoGebra Spreadsheet and paste your data. Highlight all the data, all 70 pieces of data, and find your sample mean. And so we're going to take the sample mean from that we found, because the problem doesn't give it to us. And I went 2 decimal places. You probably can go just 1, but I went 2. And then the problem gave me the rest. The problem told me that the samples, a sample of 70 random transactions, so that's the sample size. The standard deviation is 600 milliseconds, and we want a 98% confidence interval. So then we just go into GeoGebra, we change to Z estimate of a mean, put in everything we know, and out pops the data. But be careful. The other reason I wanted to show you this is see how it says round your answers to the nearest integer. So we don't want any decimals in our confidence interval. So for the first one, we want 5,907 for the lower limit. For the upper limit, we have 6,240. And there's our confidence interval. So it is a two-step process because we have to find the sample mean. They didn't give it to us, but that's okay. GeoGebra did all the work. The other thing we have to do in 8.2 is the minimum sample size. Now, GeoGebra is not going to do this for us. We're going to use the formula. What we're going to have to do is we're going to have to find the Z value from the table based on our confidence level. We're going to multiply that times the population standard deviation, which will be given, and then we're going to divide by the margin of error. We have to make sure that we remember to square this. So what you're going to do is hit in the calculator, you're going to hit the parentheses, then hit the fraction key. Go ahead and do all your work, and then come out of the fraction before you hit the parentheses and the square. Now it's going to look a little strange, but we always round up on these, and I'll explain as we get into the problem. So we are going to actually do these in our Casio, or if you have a different calculator, but not in GeoGebra. All right, let's see what we've got here. Suppose the scores of a standardized test are normally distributed. If the population standard deviation is 3 points, okay, so sigma is 3, what minimum sample size is needed? So as soon as I see that those words minimum sample size, and I know that I have my population standard deviation, I'm going to use this formula from my formula sheet. All right, so our confidence level is 90%. And then it's not going to say that the margin of error is equal to something, or it's not going to say E is equal to. It's going to use these words within. So the sample mean is within 2 points of the true population mean. So when we see within, that is going to be E. Okay, so let's go ahead and figure out alpha. Well, they told me the confidence level is 90%. So I'm going to take 1 minus 0.90, which gives me 0.10. And then I'm going to divide that by 2, because remember, that 10% is what's left over from the 90%, but I have to put half in each end, to the left and to the right. So I end up with 0.05. So I'm going to come up and grab Z of 0.05. And be careful, because there's a 0.05 and then there's a 0.005. So you've got 5 100ths, and then you have 5 1000ths. Okay, so now we're going to use our formula. We know from the table that we want 1.645 is our z-score. We know our population standard deviation, that's 3. On the bottom we want E. Whoops. Sorry, let me erase that a second. Okay, E is 2. And then we need to square. So hit your open parentheses, hit the fraction key, put in all the numbers, and then come out of the fraction. Use your right arrow key, then put your parentheses in your square. And you end up with 6.08855,625. Now, we are always going to round up with the minimum sample size because we have standardized test scores. You can't have 0.08855 of a test score. You either have 6 test scores that you're looking at or you have 7. Well, if you only go with the 6, you might short side yourself and you might not be within those 2 points of the true population mean the way you want to. It's always better to do more with sample size, not less. And so even though normally we would round this to 6, we want to always round up. And so we are going to go to 7. I know, we just got you used to all that rounding and now we changed the rules. But for histograms, we changed the rule. We always round up just to make sure we can contain all the data. And then here, we're always going to round up to be sure that we're going to meet the confidence level and the margin of error. And so we'll always be on the safe side and go ahead and look at 7 test scores. All right, let's try another one. Suppose the number of dollars spent per week on groceries is normally distributed. The population standard deviation is $7. That's sigma. What minimum sample size? So again, we know we're going to have to use that formula. With the square on the outside. We want to be 90% confident. And we want the sample mean to be within $3 of the true population mean. So within 3 means that that is the margin of error. So let's go ahead and find our alpha here so that we can find the right z-score. Looks like it's the same as the last problem. You're probably getting used to these, that you can see real quick what's going on. So we had 10% left over. That told us that we're going to have 5% in each tail. So we're going to go ahead and grab z of 0.05. Okay, so then in the calculator we have 1.645 from the z table times the 7, that's our population standard deviation. We have our margin of error on the bottom, 3, and we're going to square that. And we get 14.7328. So that one looks like it's supposed to round up. That one's not as weird looking. But even if that had been 14.132, we would still round up for minimum sample size. So we need to we want 15 different grocery totals. That's what we're going to look at in order to be 90% confident and keep our margin of error within $3. Okay, one more. Population standard deviation for the total snowfalls, oh my goodness, snowfalls per year in a city is 13 inches. So sigma is 13. If we want to be 95% confident, that's our confidence level, that the sample mean is within 3 inches, so E is equal to 3, what is the minimum sample size that should be taken? So let's go ahead and find our alpha. So alpha is going to be 1 minus 0.95. That gives me 0.05. That gives me 5%. And now I need to split that up into 2 pieces. So I actually get 2.5% or 0.025. All right. So then I grab that from the table. And now I can put it all into my formula. Z is 1.960. The standard deviation is 13. We're going to divide by the margin of error of 3 and then square that. So we can't have part of a snowfall. We either have a snowfall or we don't have a snowfall. I don't know why I can't say snowfall today. So therefore, we are going to round this up to 73 just to be on the safe side. If we only look at 72 pieces of data, we might not meet the confidence and the margin of error that we want. So we're going to go ahead and always round up on minimum sample size and therefore we're going to look at 73 snowfalls.